Okay, let's get started. Sorry for the delay. This thing took a while to set up. All right, so today we're going to be doing our midterm review. Basically how this works is I will first go through the practice exams that were released on Piazza. Hopefully all of you had a chance to go over these, or if you haven't, you probably may want to before the midterm is released on Wednesday. I already talked about the logistics of the exam. It'll be released as an overleaf link on Piazza. It's very important, as it says in the instructions here. If you have any questions about the exam once it's released, you need to ask it in a private Piazza post. If you ask it in a public post, it will be deleted. If we find any sort of error or need to make a clarification, the instructors will do so in a public post, but no student post should be public. And myself and the TAs will try to regularly respond to Piazza questions between 9 to 5 on Tuesday and, this is from the last exam, Wednesday and Thursday for this exam. So if you post a question late in the night after we have gone to sleep at our regularly scheduled bedtimes, you should not expect any sort of response. You may get one if the TAs are up late, but don't count on it. Okay, so the exam, just like in the previous, at least in this year's exam, will be 4 questions. All of them have multiple parts. The topic list we already talked about last time will be everything up to and including the very last lecture that we covered on retrieval augmented models. All right, so any logistics questions first? Okay, so also note that in case this wasn't clear, there's no class on Wednesday, so you should use that time to work on the exam. So let's get started by going through some of the problems on the previous exam. So if you haven't yet started studying for the exam, I would highly recommend to start with the fall 2021 exam. This is the course that was just taught last semester. The material is roughly equivalent, so all of these problems that you see on this exam are also potentially topics that you might see on this semester's exam. Of course, there are no guarantees, but you should be able to answer all of these questions. You should be familiar with all the concepts in them. After you finish looking over this one, then you should go over the fall 2020 exam, and then some of the topics start to diverge after that. So I'll try and go through and tell you which problems you probably shouldn't worry about from some of those older exams. But let's get started here. So I also have the iPad to work some of these through in case that's helpful. So this one is talking about prompt-based learning. So remember that we talked about a couple of different variants of this approach. We talked about the zero-shot in-context learning that is of the style of GPT-3, where you give it like a description of the task that you want to solve and then some examples of that task possibly. And you put all of that into the prefix of a language model and then give it a new example from the task and ask it to generate some continuation of that. So this approach, the language model requires no further training or fine-tuning. It's just a huge scale language model. You tell it essentially what task you want it to solve and then see how well it does. We talked about alternatives to this approach, which kind of, instead of having no training at all, they have very minimal training. So maybe we'll add a sequence of embeddings to the start of each input, and that sequence acts as a learned prompt that tells us tells the model exactly how the task looks. And so that approach, we looked specifically at prompt tuning. There were other related approaches like prefix tuning and so on that we didn't cover in as much detail. So this particular problem is talking about the prompt tuning method. So we went over this in a lecture. Essentially, we have a huge scale language model, and all of its parameters are frozen when we approach a new task, but we add a very, very small set of new parameters, which are of the form of embeddings that get prepended to every input. And so these kind of act as analogous to a discrete prompt or task description that explains how the task works. But importantly, the model is learning this prompt, so we are not manually specifying what the task should be described as. So in this case, Gilbert works for Zeta. They're making some sort of VR goggles, and he wants to know how people are responding to those goggles on Twitter. So he collects a tiny data set and has 300 tweets that mention these goggles. Each of them is tagged with whether it contains praise or not, so a binary label. And his data set is small. He doesn't want to train something from scratch, so he decides to use a left-to-right language model and adapt it to solve his task. So note that when we talked about prompt tuning, we talked about it in the context of the T5 model, which is an encoder-decoder model. However, in this problem, we are talking about just a left-to-right model, which is a decoder-only model. So you should expect to see things like this on the exam, where you might have to try and adapt a method that we discussed to a new setting. It could be one of the different variants of a transformer that we talked about, right? An encoder, a decoder, an encoder, decoder, a prefix LM, right? There are many different combinations of these things, and you should understand how they all can interact with the methods that we discussed. So in this case, you're trying to apply prompt tuning to a left to right language model. There's, of course, no change in this method. It doesn't really matter if it has an encoder, decoder, or if it's just a decoder. You're still going to be prepending some tokens to the input. So the first question is talking about his initial attempts to solve his task. He starts with some discrete prompts. So a discrete prompt is one that we, as the designers of the model, engineer ourselves. And in a discrete prompt, it's just text that tells the model how to solve the task that you want it to solve. So here, he just wrote a question like, does the following tweet praise Zeta's amazing goggles? And then presumably he would concatenate the text of the tweet and then see if the model generated yes or no. And that would be how he solved this problem. So he tries a ton of different discrete prompts. He applies a paraphrase model to get even more of these prompts in case maybe this is not the optimal prompt, but if you get rid of the word amazing, maybe it performs better because that kind of biases the model, and so on. So he'll get a lot of these different discrete prompts, but he finds that none of the prompts matches the validation accuracy of a learned continuous prompt that was obtained through prompt tuning. So the question is asking, if he were to enumerate every possible discrete prompt, so the embedding sequence is 100 embeddings long, if he tried every combination of 100 words from the vocabulary, would he be able to find one that matches the accuracy of the continuous prompt or not? So I did post the solutions, so I'm sure many of you have read those. You might note that they're very short, so they are low on details because I'm lazy. But we'll go over this in more detail. So the answer to this question is no. And that's because if you enumerate every single K-token long discrete prompt, then every choice of an embedding comes from one of the learned word or subword embeddings in your word embedding matrix. So the big language model's embedding matrix. So if you have V different word types in your vocabulary, each of the 100 tokens in this discrete prompt has to come from one of those V embeddings that are associated with that vocabulary. However, the continuous prompt has no such constraint, right? The continuous prompt, that you randomly initialize those 100 embeddings, and then you fine-tune the model such that the backpropagation, all the gradients go directly into those embeddings that you prepend at the start of the sequence. So there's no constraint that says every single one of the continuous embeddings has to be identical to one of the word embeddings in your vocabulary, right? That would be very hard to optimize. These embeddings could be anything. They lie outside the space of the word embeddings in the model, and thus you could enumerate every possible discrete prompt and still not get the same performance as a learned continuous prompt because they are in separate vector spaces. Does that make sense?
Although the continuous prompt actually does offer a lot of flexibility, but when we land up into, it could be a chance that there could be a possibility that we could land up into a local minima, right?
So the question is there a possibility that we end up in a local minima?
And we might be able to actually give it better.
Oh, sure. Yeah, so it's certainly possible that we could get a discrete prompt through our search that performs better than the continuous prompt, right? Because a continuous prompt is learned through some optimization process. As you say, it could go wrong somewhere. Maybe our optimizer isn't good, or our training data is too noisy, or in this case, it's very small, so perhaps it would be bad. But the question is asking about, will you be guaranteed to find one in any situation? And the answer is no. But yeah, practically speaking, it's unclear in this particular setting if a continuous prompt would be better than a discrete prompt. Let me see if there's any YouTube comments. All right. Any other questions on this? Yes.
One more follow-up on the same question. So we'll be fine-tuning the prompt embeddings on 300 beats which we have, right?
Yeah, so the prompt embeddings in the prompt tuning method are going to be fine-tuned on this 300 tweet classification problem. Other questions? Okay, so next, he determines that even if he could enumerate all of these discrete prompts, of course, he's not guaranteed to find one that matches the performance of the continuous prompt. Secondly, it's just not feasible to enumerate so many discrete prompts, right? So he decides to develop essentially like a translation model that, given a discrete prompt, maps to a learned continuous prompt. And so the idea is that maybe the learned continuous prompt on average is always better than a discrete prompt that Gilbert can find. But it's also good that he can specify what he wants the model to do in natural language. So maybe he wants a model that will take in a specification of a task and then output a continuous prompt which does not have these constraints of all of the token embeddings have to belong to the word embeddings of the model. So this question was just basically asking, how does he set up a model to map from discrete prompts like does the following tweet praise Zeta's amazing goggles to a continuous prompt sequence of 100 embeddings that are learned by the model and are not particularly interpretable to us. So anything that you said for this question that was like he could use a sequence-to-sequence model, or he could use a language model and fine-tune it on this task is a good start. But one of the critical questions in this particular problem is the objective function that is used to actually fine-tune this translation model. So maybe I can switch to the iPad to make this more clear. How do I do that? Okay. So this was, question 1.2. So his input, let's say he's using an encoder-decoder model, that's probably the easiest for this task, is something like does tweet praise goggles. So this is a discrete prompt, right? And of course, you can, let's say you're using T5, that is a pre-trained encoder-decoder model. You can pass this through T5 encoder, and you get some vectors. The real question is, how do you implement the decoder, which is supposed to generate these tokens of the continuous prompt? So we have T5 decoder, and this thing is going to generate the continuous prompt. Now note that the difference between this task and machine translation is that in this task, I don't actually know the identity of the words that are associated with each of these green embeddings, because there is no word, right? They're just embeddings that are learned through this prompt tuning process. So what should my loss function be? So any ideas? I can't really use the cross entropy loss here, right? Because I don't have a particular word that corresponds to each of these green embeddings. I don't have a particular label, right? Right. So remember the very first loss function that we covered in this class when we were talking about backpropagation, right? We can use the L2 loss, or we called it square loss as well. So remember that this loss function is a regression type loss, right? So it'll just basically square the difference of the two vectors, and that becomes your loss function. So yeah, that was kind of the critical question. This is not the only loss function that you can use. You could also use a contrastive loss function similar to what you might see in some of those retrieval augmented language models. But as long as you said something that was not the cross entropy loss, which is naively applied in machine translation, you got some points on this problem. Any questions? So let's say our decoder predicts this black vector at time step 1 here, and the ground truth is this green vector, which is the continuous prompt vector that has been learned by the prompt tuning process. Right, so now my decoder has output a vector, and in general, in a machine translation or summarization, we would pass this black vector into a softmax layer to classify the identity of the word that this belongs to, right? But here, we don't do that. Instead, we can just subtract take the difference between this green vector and blue vector and square it, and then we have our loss. So that's how. All right, so let's go back to the slides then. I know YouTube questions. Okay, and finally, it also says, how can he use this model to produce new continuous prompts from discrete prompts at test time? So what is one way that he could do this? Let's say he built the model that I drew on the iPad. And at test time, he gets a new discrete prompt. So he feeds it into his input encoder, but then what happens? How should he get a predicted continuous prompt output from this? So what would I do in machine translation? Right, so I would just take the output of the decoder, and how do I get a sequence output from the decoder? Right, so there are some strategies that I might want to use here, right? So what kind of decoding algorithm would make sense given that I have this new setup? Well, perhaps I could use something like, I don't know, greedy decoding or whatever to get some new continuous prompts, right? So yeah, you should have just specified that you need to still decode from your decoder to produce a new continuous prompt. Okay, and then question 3, or 1.3 here is talking about why would Gilbert ever want to build the model that we just drew on the iPad? So remember that this model takes in a discrete prompt and outputs a continuous prompt. And the training data in problem 2, he got a large data set of discrete prompts paired with these learned continuous prompts. The idea on average is that these learned continuous prompts work better than a discrete prompt, like any one discrete prompt. But on the other hand, there are some disadvantages of these continuous prompts compared to discrete prompts. So what might those be? Right, so continuous prompts are not interpretable, right? We can't easily map them into natural language to understand what exactly the model is getting prompted to do, whereas something like this, which is a discrete prompt, is obviously very interpretable, right? We know exactly what the model is being asked to do here. So that's one solution, right? The fact that he doesn't actually have to, at the end of the day, he has an interpretable, essentially, prompt that he kind of understands what the model is being asked to do. It's just getting translated into this form which the model can understand more effectively. What is another potential advantage of this approach?
You can generate continuous prompts for other discrete. You just give any kind of discrete.
Yeah, so basically you never have to perform prompt tuning again for any new task. You can instead just put in a description of how you want the model to solve the task, and the model will generate a continuous prompt embedding for that task. So prompt tuning is very expensive, right? Even though you are not adjusting all of the model's parameters, you're only learning the small set of new parameters, you still have to compute the gradients all the way back through to the final input layer where those prompt embeddings are. So it's very expensive, and if you had a model like this, you don't have to go through that optimization process. Instead, you can just use this model at test time to produce a new continuous prompt. So that's a big advantage as well. All right, any final questions about problem 1? Where do we get the ground truth green prompts for each discrete prompt? So if you look in the problem specification for number 2, you see that it says Gilbert collects a large data set of discrete prompt, learned continuous prompt pairs. And so on the iPad, those green vectors came from the learned continuous prompts in Gilbert's data set. Of course, if you wanted to do this in practice, this part would be hugely expensive to obtain such a data set, but you know, we're not actually making you do this, so it's fine. All right, so on to the next question. This one was about modifications to the transformer architecture. This is generally a theme with these exams. We've spent a long time in this semester on understanding attention and transformers and so on, so you should certainly be familiar with everything that we talked about and probably expect at least one question on these architectures. Some of the previous midterms had like, you know, compute the gradients in this network. Obviously with this kind of take-home exam, that kind of question is not a particularly good one because you could just evaluate the gradients in PyTorch and then, you know, so you're not going to be asked to actually, you know, compute any derivatives or anything like that, but you may be asked conceptual questions that rely on your understanding of backprop and so on. This question does not. So this is more of an architecture-related question that tests your understanding of batching in a transformer and masking and so on. So here, Julia has this approach to pack more context into transformer language models without overly increasing the sequence length. So why might she do this? Because transformers, their time and memory complexity is quadratic in the length of the input sequence. So as you get longer and longer sequences, the model becomes slower and slower to train and also to, at test time, to decode from the model. So we are very interested in approaches that reduce the size of the input context while still maybe representing a huge number of tokens. So Julia's method is quite simple. Normally, you would feed a language model the token embeddings associated with every token in the input prefix. But Julia decides to first aggregate these embeddings. So basically, pass each contiguous non-overlapping segment of 5 tokens. So like x1, x2, x3, x4, x5, that's 5 words. She'll pass that through BERT, a pre-trained BERT model. And we know how to represent any sort of input text with BERT, right? You can just take the CLS vector associated with the input and use that vector as a representation of the syntactic and semantic content of that input. So you can see that Julia does this. So every 5 words, she will chunk the text into 5-word segments, feed each segment into BERT, and replace the token embeddings with a single CLS token that represents all 5 of those words. So intuitively, in this method, she can reduce the size of her sequence by 5 times, right? It's just for every 5 tokens, she now has 1 vector. So this is obviously nice from the perspective of the complexity of the model. It'll practically be faster. However, there are some issues because she wants to use this model as a language model. So let's try drawing what this looks like on the, why is my Zoom open? On the iPad. All right. So this is question 2.1. And so here, let's assume we have these x1, x2, x3, x4, x5, and then x6, x7, x8, x9, x10. So each of these, we are first, this is like a pre-processing step for her. We're going to pass through a BERT, and that means that each of these will be augmented with a CLS token, right? Because we need to get the vector representation associated with that. We take the corresponding CLS token vector. And so now this is segment 1's representation. This is segment 2's representation. Similarly, she'll get segment 3, segment 4, and so on in this way. So she has a fifth of the original vectors by using this compression method. Okay, so let's say she does this. Let me move this up. This is just an illustration of the what is described in the problem statement. Now, she wants to train a language model using this kind of input representation instead of what we saw before. So concretely, her input is going to look like S1, S2, S3, S4. But she, if you note in the problem statement, she wants to use this model for next token prediction, not for next segment prediction. So that's where the challenges lie. So let's say I put this thing through a transformer. And doing so, I'm using masked self-attention, right? Because this is a decoder-only transformer language model. So I get these segment-level vectors. Now, let's say I'm given this representation for S4 here, this one. How do I use this to predict the next word here? So what would be the next word here? It would be like X21, I guess, right? How do we use this to predict X21? What are some ideas? So how would we predict x21 normally if we didn't have these segment vectors and instead we just had token level vectors at the final layer? You have an idea? Yeah, right. So in a token level model, this input here would be x20, right? And then we would get this representation, and then this would be passed to a softmax layer to predict x21. On the other hand, in this case, the current representation is actually S4, which corresponds to x16 through 20. So if we pass this through a softmax layer to predict x21, that's fine. We can do that, but how do we predict x22? x22, the representation here, we can't just shift forward to S5 because S5 represents x20 through 24. So now, if we try and predict using this vector, x22, we are actually leaking information about the identity of x22 because the input is already a function of x22, right? So one of the issues with this whole setup is that the input representation scale does not match the output representation scale. And if you just naively use a transformer language model, you're going to run into this kind of cheating problem where your input already contains information about the word that you're trying to predict. So one possible solution, which is not great, but which you could do, is at each segment representation in the final layer, you could have a different softmax layer to predict each of the 5 next words. So given this segment level representation, I could pass it through softmax layer 1 to predict x21. I could pass it through a different softmax to predict x22, a different softmax to predict x23, and so on. And only after I've completed all of the tokens in the next segment, only then do I move forward in my language model and start predicting the next 5 tokens. But this approach is not great. Does anyone who followed along have any issues that they identified with this approach? So I'm trying to predict 5 tokens from one segment level representation. What could be some issues with that? Yeah, go. Yeah, exactly. So we're breaking all the dependencies between the tokens in the same segment, right? So the prediction accuracy, the perplexity of this model would be really bad as a result of that. Yeah, so the second question asks, if she wanted to use this segment level representation, and if computational constraints were not an issue, how could she actually make this work without this cheating problem or without breaking the dependencies between words in the same chunk? So one approach is just to modify the data. So let's say I wanted to predict, so this is for Q2.2. Let's say I wanted to predict x21. I would feed in S1, S2, S3, S4 as inputs, and this, I'm not cheating. If this is my input sequence, I can predict x21 because it's the immediate next word, right? The challenge is what happens when I want to predict x22. So here, if I feed in the exact same input, then I don't actually have any information about x21. So the model won't be have the immediate previous word to make this prediction. So what you should be doing is recomputing this. So basically, I have S1, S2, S3, S4, and then I have a new S5 segment representation, which is a function of just x22. sorry, just x21. If I want to predict x23, then I have S1, S2, S3, S4, and then another segment representation, which is a function of x21 and x22. So basically, to get this, you would just have to feed in these individual segments to BERT to get different representations of that fifth segment that don't actually include the word you're trying to predict or the future words. So, of course, this is not an efficient solution, but the question didn't ask you for an efficient solution. So this is the easiest of solutions that you could have come up with. Okay, any questions? Yeah, the same BERT. So remember, that is just a pre-trained BERT. It will give you a CLS token for any text input that you feed in. It doesn't have to be a 5-word chunk. It could be a 2-word. It could be a 128-word chunk. You can still get a vector out of it. Okay, great. Let's see if there are any YouTube questions. Nope. All right, so let's move on to the next problem here. Right, so then the final part of this problem asks you to shift from token level prediction to segment level prediction. And it frames it as a retrieval task. So this is kind of testing your understanding of the retrieval augmented language models that we saw in the previous lecture. So here, Julie is given a sequence of segment representations, but instead of predicting the next word, she's asked to retrieve the vector associated with the next segment from the set of all possible segment vectors that are in the training set. And so, inspired by things like Realm, we asked you, how would she set this thing up? Actually, a lot of people went wrong on this problem because they just copied all the equations from the Realm paper for some reason. This problem does not ask you about language modeling at all. There's no word prediction here. Your only goal is to perform retrieval. So basically, all you need to do is encode all of the segments in your training data and then set up a kind of retrieval-based objective function. So basically, you could have an objective that maximizes the dot product between the segment embedding associated with, say, SI after feeding it to your transformer, and the ground truth segment embedding of SI plus 1, and minimize the dot product of this embedding with all of the wrong segment embedding. So that's all you really needed to say. But any sort of objective that kind of maximizes the score of the context with the ground truth, the next segment, and minimizes the score of the context with all the other segments is fine. You could even treat this as a classification task. We didn't tell you this has to be efficient at all. So you could have even set this up like with a softmax classifier. All right, any questions about this problem? All right. So let's move on. This was probably the trickiest problem on this exam. It is asking about tokenization and your understanding of, because we had a whole lecture on tokenization, right? We talked about tokenizing with words first, then we moved to subwords with byte pair encoding. Then we talked about things like characters and even bytes as the lowest form of tokenization. The lowest level form of tokenization, sorry. So in this problem, Terry decides to train language model on a popular language modeling benchmark task, Wikitext 103. This is just some random articles from Wikipedia. But instead of settling on a tokenization beforehand, like word level or byte level, he decides to randomly tokenize the input using a mixture of all of these possible tokenizations. So given an input sequence from the training data, he first chooses a random segmentation of the sequence that can mix multiple tokenization schemes. So given the sequence, the evil warlock, one plausible segmentation that he could select is like a word level tokenization. So the space, evil, space, warlock, or a mixture of tokenization. So THE space, the entire word evil, space, the subword war, and the subword warlock. So this is mixed character, word, and subword tokenization. And this is all a completely random process, right? So every time he sees this training example, he might see a completely different segmentation. That's the general idea. However, he has just a single language model that is expected to predict the next word given any of these segmentations. And the next word here is poorly defined. It's not always a word, right? Depending on the segmentation, it could be a character, it could be a byte, it could be a subword, or a word. So the vocabulary of the language model includes every byte, character, subword, and word. So it is capable of predicting any of these things. The language model is trained using next token prediction and updated through backprop. So let's call his model LMA. LMA is trained on these random segmentations. And then he has a baseline LMB, which is trained using word level tokenization. So now he wants to compare which model is giving him a better estimate of the probability of this sentence, language models are stupid. So to do this with language model B is very simple, right? Language model B only has one tokenization. It's a word level tokenization. So you would split the sentence into language models are stupid, and you can compute the probability of the sentence under language model B. How would you do that? What's that? Well, you have LMB, which is a, let's say, well, I guess we didn't specify what it is, but it's some sort of language model which is giving you the probability of word X given all the previous words. So how would we use that model to give us the probability of this entire sentence? Yeah, exactly. So we would just use the chain rule, right? And we would get the probability of this entire sentence. So now with LMA, it's not as simple. And that's because and many people wrote, well, we would just randomly segment this sentence because language model A is using random segmentation. And then we would apply the chain rule to compute the probability of that sentence. What is an issue with that approach? I mean, that's how the model is applied during training, right? We pick a random segmentation, and then we simply just compute the probability. So that's not an issue. It says, assume there are no out of vocabulary issues associated with this sentence. Yeah, exactly. So language model B, there is only one tokenization that is ever possible of this sentence, right? Language models are stupid. So thus, what we just described for language model B is sufficient. Language model A, there are many possible segmentations that the model could see of this sentence, right? Each one of those segmentations, the model will assign some probability to. Right? It's not like in language model B where there's only one segmentation. Here, the total probability of the sentence language models are stupid is distributed over all possible segmentations of that sentence. And so to correctly compute the total probability of the sentence, you have to sum over all of the possible segmentations that you get here. So of course, this is not really feasible given the this is just arbitrarily mixing different tokenization. There are many possible segmentations, but that's what you should do. And it's not fair to compare just one random segmentation of the sentence, the probability of that, to the probability of this word level model, because you will actually get a much smaller probability mass on any one segmentation of the sentence than you would for language model B, because there's only one possible segmentation of that sentence. So this was I don't know, I guess it turned out to be quite a tricky problem, but it is actually a realistic scenario, especially when we deal with these models that could theoretically mix tokenizations. In fact, yeah, go ahead. That's a good question. So what if we have LMA, we train it in this way, and then we fine tune it using only word level tokenization? I suspect that then, like, depending on the fine tuning parameters, the model would become specialized to word level prediction, and then yeah, I guess you could make a nice plot comparing the probability mass that is placed on the word level tokenization of the sentence as you increase the number of iterations of the fine-tuning process. It probably will go up, and the probability assigned to any other segmentation will go down, but it would still be non-zero. What I was going to say is, when you do something like byte pair encoding or sentence piece, you already have the option to have multiple tokenizations, because in, say, byte pair encoding, the base vocabulary is the characters that are associated with the language, right? And then you form subwords out of these characters, but you can always form the same word by just using the base characters as well. In the actual implementation, you tend to favor segmentations with as few tokens as possible, so you'll probably never see a sequence represented by just a character level tokenization when you're using something like BPE, but it's still possible. This is just like a much more scaled up version of the problem where these multiple tokenizations are getting mixed regularly. All right, let's continue then. So this problem was more of a kind of system description problem. You can expect one of these as well, where we give you some task and tell you to design a model and fully specify like the input-output format, the training objective, the architecture you'll use, how will you evaluate, and so on. Note that there was already another problem that was similar conceptually, which was, this one, 1.2, where we ask you to describe this whole pipeline for this particular task as well. So, you know, in NLP, it's important to at least know what kinds of models and objectives are best for what kinds of tasks. So here, this was a machine translation task. It was a little bit more complicated than that. So basically, you have this book, it's written in Korean, but you don't know how to speak or read Korean, and there's no professional translation you can get. So you just put this book on Google Translate, and you get an English translation out of it that way, although it turns out that the story is not readable because the Google Translate has made severe errors. So you really want to read the book in a better translation, so you try and improve the translation process. This is also an example of a question where we introduce a new concept that you have to kind of learn about. Post-editing is a process where you train a machine translation system, and you get people, real people, to correct the output of the machine translation system. And then you can train a model on top of the corrections that you get, so that that's called a post-editing model. It'll take the output of any MT system and then perform some corrections to improve the quality of the translation. So we basically ask you to make a model for this post-editing process. It's kind of specified here. Given a Korean sentence and an English translation of the sentence produced by Google Translate, your model should produce the corrected English translation. So given these kinds of inputs, I mean, one part of this is how do you even get the corrected English translation? We tell you you have this in your data set, so you don't need to worry about it. But basically, how do you actually train a model for this task? Since you now have two different inputs, you have the original Korean sentence, and you also have the noisy Google Translate version of the sentence. So we gave you a big hint that you might want to use a multilingual language model like Byte T5. Why might you want to use a multilingual model like Byte T5 for a task that has these kinds of inputs? Right, so the input is in two different languages. So you can't really just use a model like GPT-2 or GPT-3, right? Because the vocabulary is all in English for those. And it might not even have the necessary characters to represent Korean. So you also want a model that's capable of understanding multiple different languages in the same model, because we don't want one encoding of Korean and then one encoding of English and then somehow merge them together. That's definitely possible, but now we have a much better way to do this with a single model. So in Byte T5, we don't actually do anything special, right? We would just maybe concatenate the Korean sentence together with the Google Translate and feed it into the encoder of Byte T5, right? That's very simple. And then the output would just be the corrected English translation. So there was really nothing that you needed to do here except specify the input-output format. Yeah. And then this question was kind of open-ended. How would you evaluate whether your model is actually succeeding at producing better translations than Google Translate? So there are many human evaluation metrics that you could do, right? You could ask experts who speak Korean and English to judge the outputs of your system compared to Google Translate. You might also use some automatic metrics to compare whether Google Translate is better than your model output compared to the reference translation. So there's many different things that you could do. All right. I'm not sure what this comment is referring to, so let's move on. Are there any questions about this problem? All right, so yeah, if you were unsure about any of the stuff we covered here, you should try and work through these problems and make sure you have an understanding of them. So let's go through. Was this the fall 2020 exam? What was this? Yeah, this one. Fall 2020. So a lot of these problems are also relevant and a totally fair game for this semester. We only have 20 minutes, so I'll go over them faster. Yeah. For the evaluation part? I mean, you could use back translation to perhaps augment your training data. But yeah, I mean, the data set collection process, initially for this problem, we intended people to have to mention that you need to, if you have a parallel data set of the source novels paired with the English translations, we actually wanted the students to figure out that you actually need to align the sentences in each of these novels first before you have a data set. But our wording was too vague, so we didn't end up evaluating that. But yeah, like the very first thing you would need to do here, if you just have a Korean book and then an English translation by a professional, is figure out which sentences in the Korean book align to which sentences in the English book. And that there are many different methods that you could use for doing that. But once you have a data set like that, of course, you could use some back translation type approach to further augment your data. But here we had this word large, which probably indicates that it's not important. Okay, So let's go over this problem in particular. So I will also say that this exam from fall 2020 it turned out to be much harder than the exam from last semester. It's very hard to predict how difficult any of these things will be, so I'm not sure how hard this year's exam will be. I guess we'll find out soon. Anyway, so in this question, we were playing around with the different transformer mask strategies so that it was really testing your understanding of whether you understood why we have this kind of lower triangular mask in a transformer language model and what happens if you manipulate that mask. So we have this mask, of course, because we don't want the model at each time step to see any tokens in the future, right? Because it's trying to predict the next word. But Sarah changes this mask to what she thinks is a trigram model. So remember, in a trigram model, you are conditioning your prediction of the next word on only the previous two words and no other words. So if you look at this mask, you're only ever attending over the previous two things, and all of the other tokens here are set to 0, meaning you're not actually attending over these tokens. So she reasons that this new mask allows the model to only attend over the previous two tokens in the decoder, but she finds that after she trains the model with this mask, the perplexity of the model is actually quite good, and it's just a little bit worse than the model trained with the full mask. And so the question is asking, why is her validation perplexity much lower than expected? So to answer this question, first you have to understand the premise of the problem, which is that the validation perplexity being low means the model is doing better than she expected, which means that perhaps the model is not actually a trigram model, because if it actually were a trigram model, it should be doing much, much worse than a model trained with full previous context, right? So how is this language model leaking information beyond the last two tokens, given that at every layer, the attention mask looks like this? And the answer is that because you have multiple layers here, you are not just modeling the last two words at every layer. At the first layer, you're definitely doing this, but then note that after the first layer, every token now has information about the previous two tokens in it. So at the next layer, when you look at the previous two tokens, you're actually looking at a longer context window. Your receptive field essentially has increased, and as you stack more and more layers, this mask, even though it says that you're only looking at the previous two vectors, those vectors are functions of many more tokens in the input. So the number of tokens that it's a function of scales linearly with the number of layers that you have. And that's what it was asking. So this turned out to be quite tricky. And the next question asks you to fix this problem. So how would you actually make a transformer trigram model? And one way, which is pretty straightforward, is to just change the data format. So if you only ever feed as input two-word sequences and ask the model to predict what happens next, there's no way for it to look at any information before. There also was a hacky solution where you can use the mask that she used at layer 1, and then at all subsequent layers, you can change the mask to a 1 at the current time step and a 0 everywhere else. So this would also be a trigram model in that it's only ever looking at the previous two words and only at the first layer, but it's only doing the self-attention at this first layer and not at any of the other layers. But we accepted that solution as well. All right, any questions about this? Whoops, which one was I on? Okay, so finally, we had a question asking you to compare the training time of your solution versus her original flawed approach. So her original approach does not change anything regarding the complexity of the training time, right? She just modified this mask. Your approach, if you use the data modification, will probably be much slower than hers because you're going to have many more examples than her approach because all of your examples are 2 words long. So for one input sequence, you're going to have to chunk it up into many different 2-word sequences. And even though each sequence is a lot shorter than the single one in Sarah's model, you have so many of these that that's going to overwhelm the, like one batch is going to consist of probably just these 2-word chunks from one sequence. So this was more of a practically oriented question. If you did this solution though, where you just modify the training mask at layers 2 through 16, then there's no change in the complexity. All right, so let's see, we have 10 minutes left. This problem was another of the, here's a new task, how would you solve it with the models that we've covered in the class. I won't go into any detail here. You can look at the solutions, and it also asks you how you evaluate this. This was a question that also turned out to be quite tricky, which was testing your understanding of backpropagation, essentially. So here, we also introduced this concept, which we didn't really talk about in the class, of autoencoders, which are trained to reconstruct their input. So Erwin is training this autoencoder to learn representations of sentences. His model is very simple. It, given an input sentence, just computes a single vector of the sentence by summing all the word embeddings associated with the words in that sentence. So if you sum these word embeddings, you get some vector A, which is a representation of that sentence. And this is the thing that you're trying to reconstruct in your autoencoder, the sum of embeddings. So in an autoencoder, what's commonly done is you have this bottleneck representation, which is of a much lower dimensionality than the input. So the idea is that all the important information in the input, the information that's actually important, will be preserved in this low dimensional representation, and all of the unnecessary information will be thrown away. So maybe you have just enough information to reconstruct the sentence, but nothing more. So he applies a linear layer on top of this vector A, which is a 128-dimensional vector. And this linear layer projects A into a 10-dimensional bottleneck vector, which we call B. So this is much smaller than the original input dimension A. Finally, he projects this bottleneck vector B back into the dimensionality of the original input. So we have this A prime vector, which is 128 dimensional, and we just use the square loss to train our model. So we take the element-wise difference of the original input vector A and the reconstructed version A prime, and compute the square loss using these 2 different vectors. So this is how the autoencoder works. And now there's some description of his training setup. So he randomly initializes all of the parameters of the model, including the word embeddings, which is the forming vector A, right? It's the sum of the word embeddings, and the weight matrices. So we have one that projects the input into a 10-dimensional space, and another which projects the 10-dimensional vector back into the 128-dimensional space. So he begins training this network on 1,000 sentences, and the training loss quickly goes to 0. But at test time, he uses it to encode some of the sentences in his test set, and all of the bottleneck vectors, the vector B here, are identical. So he's wondering why this happened. And so this is a pretty common degenerate solution for these kinds of autoencoders, where if you're jointly training the input along with the weight matrices, the model is just trying to minimize this loss function, right? So it doesn't actually care that all the sentence embeddings should be different from each other. In fact, the easiest solution is just to make all of these input word embeddings 0, right? Because then the sum of the embeddings will also be 0. And then it doesn't actually matter what is in these weight matrices because everything will just be 0. The loss will be 0, and it's trivially optimized this objective function without actually learning anything useful about the word embeddings themselves. So this is a kind of tricky problem. We didn't ask the follow-up, which is how would you fix this problem? Does anyone have any ideas on how you could avoid such a solution? So if you're allowed to change something about the problem statement.
Adding some constant parameter in equation.
Okay, so what do you mean? Like I would add some number to each of the word embeddings?
Yes, adding some factors like that we have equation like that b equal to 10 and some I will add some constant parameters. So in that way we avoid having all zero.
Sure, so then the model might not learn all zeros, but it could learn to just converge to that positive parameter, right? And all of the vectors could be the same. So that solves one issue, but maybe not the underlying issue. Any other ideas?
Change the loss function in such a way that the zero is not happening.
So,
Like mean square, so if I did like you said, if a is equal to ai, so the error is like minimal. But if the function is designed in such a way that there is no zero coming from any combination.
Okay, so maybe you could adjust the loss function to prevent both of these vectors from going to 0 or something like that. A simpler solution is, well, why don't you just not train your word embeddings at all, right? And then you probably would never get this kind of degenerate solution. Actually, what should happen in this setup, if you really wanted to do this, is to pre-train your word embeddings on a separate kind of objective function and then keep them frozen and then learn just these two weight matrices. But we didn't ask you for this. We also didn't even cover word embedding learning in this class, so that wouldn't be relevant anyway. All right, and this one was talking about extracting facts from BERT. So we talked a lot about how these language models are memorizing facts from their training data sets. So here, this was basically testing your understanding of subword tokenization and how would you actually pass things as input to a model like BERT. So if you passed in Harry Potter's social security number as this into BERT, the pre-trained BERT model, right? Remember the pre-trained BERT model is using a subword level tokenization. So when Voldemort feeds in the sequence Harry Potter social security number is mask, because he wants to know what the mask actually is, he wants to recover the social security number, that number is not just one mask token, right? This thing is definitely not a subword in BERT's vocabulary. It would probably be split into like 9 different characters. So this would probably just, if you look at the softmax distribution for this mask token, would probably just give you like one number or something like that, which is definitely not what you want. So he obviously failed in his plan to extract the social security number because he didn't realize that the social security number should be split across multiple subwords. The next question is asking, so he managed to fix this issue somehow, but the model is still not able to memorize the social security number, and so he decides to add 30 copies of this sentence to BERT's training data and then train the whole BERT model, including this sentence 30 times. So maybe this is in the vocabulary now. And it's still unable to memorize this. So this question is asking, if you wanted to design a BERT model that is more capable of memorizing social security numbers, what modification to the architecture or objective would you need to make? And this is kind of associated with some of the stuff we talked about with the realm model, where to improve the training of the retriever, they masked out things like entities and dates because those are highly associated with benefiting from retrieval. So here you could change your masking function to only mask out numbers or mask out contiguous spans of numbers. And in this way, the model might learn to memorize these kinds of social security numbers in a more effective way. Finally, Voldemort is able to reproduce the social security number at last, although the method only works when he gives it this. Harry Potter's social security number is blank. When he gives it the social security number of the unskilled wizard Harry Potter is, he doesn't get the same social security number. So why is this happening? Because the model is likely just memorizing this prompt that he gave it 30 times the same thing. It didn't actually generalize to the meaning of this overall prompt. So he might be able to fix this by including more paraphrases or something of this template before putting it into his training data. All right, any questions about all of this? So I didn't go over any of the problems in the previous exams. Many of them are not relevant. So like in this exam, we did not cover HMMs or feature engineering, so you can ignore those. Some of these problems are actually useful to go over though. So you should at least be able to compute these derivatives, even if we're not gonna ask you, because we might ask you questions that involve your understanding of this algorithm. This problem 3 on the 2020 exam is totally fair game for this exam as well. It's asking you about recurrent neural language models, which we definitely covered in class. And again, recurrent neural networks for machine translation. As you can see, this exam was written maybe before I actually started covering transformers in the class, but we did cover RNNs quite a bit, so you should be able to answer those questions. All right, so before I end, again, there's no class on Wednesday, and my office hours for the week are right after this class, so they'll be held in my office and on Zoom from 4 to 5. Both of the TAs have office hours tomorrow. Their hours are on the Piazza post. So all 3 of us will have office hours before the exam. And yeah, good luck with all of your study.